Compute eigenvalues, eigenvectors, and generalized eigenvectors of this matrix if there is any. So I is this matrix, find eigenvalues. So lambda is an eigenvalue if determinant of A minus lambda I is 0. A is this matrix, so A minus lambda I, 1 minus lambda, 2, 0, 1, 1, 2, 0, minus 1, 1. Determinant of this. Let's do factors expansion along the first row. 1 minus lambda, 1 minus lambda, 2 minus 1, 1 minus lambda, minus 2, 1, 2, 0, 1 minus lambda, 1 minus lambda, 1 minus lambda square plus 2, minus 2, 1 minus lambda. So we have 1 minus lambda in common. 1 minus lambda square plus 2 minus 2. 1 minus lambda cube. So we have this one equals 0 if and only if lambda equal to 1. So 1 have algebraic multiplicity 3. Now we find eigenvectors. The eigenvectors V is an eigenvector associated to lambda if A minus lambda I times V equal to 0. A minus lambda I. So this is a matrix A minus lambda. Lambda equal to 1. Which give us 0, 2, 0, 1, 0, 2, 0, minus 1, 0. V, let's say for the moment ABC, V equal to 0. We do the row reduction for this coefficient matrix. 0, 1, 0, 1, 0, 2, 0, 1, 0, so 0, 0, 0. Let's switch first and second row. This one multiplied to ABC equal to 0, 0, 0 gives us A to C, B, and C is then 3. A minus 2C, B 0, C is 3. A minus 2C, 0, C. Minus 2, 0, C. We can choose any C such that C is non-zero, so we have a non-zero vectors. That one will be an eigenvector. So an eigenvectors associated to lambda equal to 1. Lambda equal to 1, right, is V1, call that V1. Minus 2, 0, 1. Now from V1 we get V2. Definition of we are missing 2 eigenvectors, so we have we need to find the generalized eigenvectors. So we have two of them, a minus lambda I square v2 equal to 0 and a minus lambda I cube v2 v3 equal to 0. In this case, this one is a zero matrix, and we also have that v a minus lambda I v2 will be v1 and a minus lambda I v3 is v2. Two formula together with the fact that v1 is the actual eigenvectors, or a minus lambda I v1 equal to 0, explain why we have the red formula here. So a minus lambda I square v2 is then a minus lambda I times a minus lambda I times v2, but a minus lambda I times v2 equal to v1. But a minus lambda I times v1 is 0 because v1 is an eigenvector, so this one is 0. So that's explain the first equation. I cube v3 is actually a minus lambda I square a minus lambda I v3. A minus lambda I v3 equal to v2. So this is a minus lambda I square v2. But as we have shown here, this one square times v2 is 0. This is 0. So from the three equations, we can deduce the two equations here for generalized eigenvectors. So that's it, just good to know. Now we have on actual eigenvectors v1. We want to find the two eigenvectors, two generalized eigenvectors v2 and v3 matrix. So v3 can be chosen to be any vectors, but we need to make sure that the chains will last until v1. We do not want, first of all, we do not want v3 to be the actual eigenvectors v1, because if it's like that, it is the actual eigenvectors, it's not the generalized eigenvectors anymore. Second of all, we do not want v3 to be in the null space of this matrix, because d here equal to 0. Then the chain will stop right here. So one easy way is that choose v3 so that it is independent from that. There are already three possibilities, say. We know 1 0 0 0 1 0 0 0 1. So you can choose either one of the three. So you just need to make sure that if we have v3, we can build back to v2 and v1, just to make sure that the chains last. If the chains last until v1, so when we multiply this to get a vector, you multiply this to get another vector. The last vector, the vector v1, is non-zero. That would be the perfect chains that we need to create. We have one actual eigenvectors and two generalized one. So in our case, we know a minus lambda I cube equal to 0, the 0 matrix. So a minus lambda I cube v3 equal to 0. So v3 can be chosen to be anything. Choose v3 to be, in this case, let me choose 1, 0, 0. Choose v3 to be 1, 0, 0. So that is first, it's independent from v1. And now we just need to make sure that we can get v2 and v1 where they are non-zero. We don't want the chain stopped in the middle. So now v3 is that, then we know v2 can be computed as a minus lambda I times v3. So we choose the first column of a minus lambda I. A minus lambda I. This matrix times v3 gives us the first column. 0, 1, 0. Now we get v1 is a minus lambda I times v2. A minus lambda I times v2. In this case, let's give the second column. It works nicely. 2, 0, minus 1. Yeah, so it's perfect. So now we update the v1. It's a minus of these vectors. So we have v3, v2, and v1. So that's, we do the lazy way where we start from this zero matrix and build back, just to make sure that at the end we do get non-zero vectors, v1, v2. There are two other methods. You use it two sets of formula. If you use the first formula sets, what you do is you raise power 2 of this matrix, find the kernel of that or null space of that, you get v2. Make sure v2 is independent from v1, and then find v3 so that it's independent from both v1 and v2. The second ways you can do is that you use this 1, 2, and 3 formulas right here. You know from the first formula v1 we found that v1 is this vectors. From v1 you can solve this equation to get v2, and from v2 you solve this equation to get v3. So that's the other one, but you need to solve two extra system of linear equations. So that will be a lot of work. So one method, easiest way here, we just use these properties so that we just to make sure that we choose v3 so that the chains will last until v2 and v1. So that will be a quick, easy way to do that.